Okay, so I'm going to go through an example of naive Bayes classification, and what that hinges on, like it shows here on the screen, is the idea that things can be statistically independent. We just saw from the previous video, this is the second one for the week, the previous one introduced some definitions, and if we were calculating the likelihood of item 1 and item 2, if they happen to be statistically independent, then it's easy to calculate the likelihood because it's just the likelihood of one item times the likelihood of the other. So you can replace the ands with multiplication. That's a nice thing. The reason the Bayes classifier here is called naive is because it's so simple. It does assume statistical independence. So in the notes, I go into detail or warning or ranting that, well, if that's not the case, you better not use it, or at least you better be careful and get rid of some features. But it's naive. It makes that assumption. The thing is, even when that assumption is not valid, it kind of sometimes works really well. And it's super simple. It's super fast. It's all based on counting. And so you guys could write a Java program if we had 1 week left, and I made you do that, which I would if we had a week left, but we don't. You guys could write a Java program that implements this, and it would be just as fast and just as good as what we have in Wicca. But anyway, I digress. It's very popular because it's simple and it gives you good results. So it's kind of like the one rule in that regard. Here we're using the weather data set, the whole thing, and we have 14 instances in it. That's a little different than the one you see in the notes because not all 14 actually fit on the screen in the notes, but I'm more sophisticated here. But in this one we have all 14 instances. So just be aware of that if you compare with what's in the notes. So I've also written down the cover of our two classes that we have 9 of those 14 for play is equal to yes, and then 5 out of 14 for play is equal to no. So we have our training data here, the ones that we know, but then we get a new instance in, and it has the values of rainy for outlook, hot for temperature, and so on, like you see on the screen. The question is, how are we going to classify it? Well, what we do is we're going to compute the probability that it's yes or no, given the values that we have. So this is an example of what we saw in the previous set of slides was conditional probability. And so the whole problem with this is, or the whole thing that if you think about it, it throws people for a loop, and so maybe it's best not to think about it, is, well, we actually don't know what these values are. We don't know the probability that's yes or no. If we did, we would just pick the biggest one and be done with it. Instead, we have to calculate these conditional probabilities. And that's kind of where naive Bayes comes in, and actually where it gets its name. But I think everybody can agree, even if you don't really like probability, that if we get, well, a probability of 0.8 for yes with these values and 0.2 for no, because remember, these should sum up to 1 if we do this right, then we're going to say, oh, well, yes is 80%, no is 20%. We're going to go with yes. So everybody's okay with the fact that we would choose the larger one of these. The only detail is, well, we actually don't know the answer. The neat thing is we can assume statistical independence. And so that means for every one of these features, we can let each feature vote independently. We can replace all the ands by multiplications. And so we can compute this conditional probability as a bunch of individual ones multiplied together. So if you're careful, if you're astute, you know, there's always things in textbooks where they say, like, the careful reader would notice at this point. So there's a little bit of magic going on. The thing that's true has flip-flopped around in here. And the reason we can get away with that is because of something that's kind of super important that I would be remiss if I didn't try to teach you this semester, called Bayes' theorem. And that shows up on the homework, how we can actually do this. But this is kind of the thing that lets us calculate that correctly. Bayes' theorem is really kind of a mathematical sleight of hand that lets you take something you don't know and calculate it in terms of things you do know. Because what we saw in the previous slides is that we can calculate all these conditional probabilities. So given the fact that play is yes, means we're dealing with only 9 of the 14 instances. So the way we're going to calculate these likelihoods, they're all going to be fractions that are divided by 9, because they're all given that play is equal to yes. That's the subset we're dealing with. So out of these 9, how many have the value rainy? So 1, 2, that's it. So the likelihood that it's going to be rainy, given that we're playing, is only 2/9. We're not very likely to play when it's raining. What about the likelihood it's hot when we're playing? Okay, here's one instance right here. So we have one. I look at all the other yeses. I see one more. So same as with rainy, 2/9. So we're not likely to play when it's hot or when it's raining so far. Okay, what about the likelihood that humidity is normal when we're playing? So we look at the yeses, and okay, so one normal, two normals, three normals, four normals, 5, 6. Okay, so it's much more likely when it's normal that we're going to be playing 2/3, 6/9. Finally, we look at the last column. Out of all the yes instances, we count the falses. So 1, 2, 3, 4, 5, 6. And so what we end up with, if we multiply all those things together, is really a god-awful mess. Who knows what this thing is equal to? So I'm just going to do numerator and denominator separately. So 2 times 2 is 4, times 6 is 24, times 6 is going to be 144. So check out the brain on Chris there. And then we're going to get 9 to the 4th power, and really, who knows what that is? I'm not even sure that number can be calculated, but I do know it's going to be 81 times 81. So we're going to get some number here, and we'll save that big reveal for the end when we'll get the calculators out and actually figure it out. This is the likelihood that, given what we know, that play is going to be yes. One thing I want to emphasize, and this is said in the notes, that there's actually something missing here. If we really use Bayes' theorem, there's a denominator here. So this is not really a probability, but this is the number that we can compare. And so this is the number we would actually compute if we were writing a computer program to do this. And so this is what we can do on the homework. But there's a little bit missing here. There should be a denominator that's going to be like this thing here. But you didn't just see that. I didn't write that there. So moving on, what we need to do now is we need to do the same thing, except we need to do it with the no classes. And so we saw that the support of no, there were 5 of them. So we have a little bit easier job in this case. We're going to multiply all those out, and we're going to get a denominator that's 5 to the 4th, which is 25 times 25. And actually, I do have to know that's 625. So I have better hopes of being able to do at least this one in my head. So let's find the no instances to make our life a little bit easier. There's all 5 of them. So out of these no's, how many have rainy? Here's 1. Here's 2. That's it. So 2/5, 40% likely to not play, when it's rainy. How many have hot? So here's 2. And that's it. So once again, 40% likely to play when it's hot. Because of statistical independence, we might think 40% likely for 2 of them. That's great. But we're multiplying these things out. So 40% of 40% is actually 16%. So with every one of these, the likelihood goes down in some sense. It only matters which one's going to be bigger at the end of the day, yes or no with this. So we do the same thing now, normal and no. There's 1. That's it. So 20% likely, even smaller. Then finally, false and no. We've got 1 up here. And 2. Okay, so 2 out of 5, 40% again. So I multiply these all together, and I get 8 out of 625. So let's figure this out. Let's see what we got for yes. I'm going to freak you out for a second. I'm going to go back to the other screen. 144 over 81 squared. That's what we have. So basically what we want to do is we want to turn these into actual numbers. You know, fractions aren't real numbers. They're the devil's diagrams or something like that. Okay, so I have on my trusty Hewlett-Packard calculator from the 80s. They don't make them like they used to. And what I get for the likelihood of yes, and I'm going to put likelihood in quotes because this is not normalized, remember. So I get 0.219. For the likelihood of no there, let me calculate that, 8, 625 divide Is it 0.128? So all we have to do at this point is we have to compare. This one is twice as big. So this is our decision. This is what naive Bayes comes up with. We still don't know the actual likelihoods. If we happen to need to know them, like say because old man Kimmer asked you on the homework or something like that, then what we have to do is we have to normalize these things. So we had two values. Yes was something like 0.219. No was 0.128. And what we know is that these two things add up to 1. And so all we have to do is we have to take the yes value and then divide it by the sum. And you can see that I don't have time. I'm too busy to write all the things here that are true. But what this is this is rainy and hot and normal and false. I think that's right. These are all our instances ANDed together. So this is the original thing that we were trying to calculate. So if we do that, and the suspense is really killing me, then what we're going to end up with is my ability to think has left for the day, ladies and gentlemen. That what we're going to end up with is for play, we're going to get 0.63. For not play, for no, we're going to get a 0.37, so 1 minus the likelihood of yes. But we picked the bigger of them. We didn't have to do this normalization because the bigger one doesn't change if we don't normalize it. So we could have stopped one step before if all we needed was an answer. But that's the nice thing about naive Bayes, is that it's very simple. It's even conceptually simple. If we can count and multiply, we can do this stuff. If you dig into the math of it, then it becomes a little bit mysterious, and that's something if you ever took another data mining course like in grad school somewhere, you would definitely see more of this, because this is kind of where a lot of other more fancier ideas in data mining begin. But naive Bayes is important, Bayes theorem is important, and this is our overview of it.